This is the second video in Taylor's and Maclaurin series. So far we have learned Taylor series, or Maclaurin series that is, for e to the x, sine of x, and the cosine of x. And we've been looking at some applications of these Maclaurin series. We're going to look at one more here. We now want the Maclaurin series for the sine of x over x. If we go to the definition, which says that the function is the first derivative at 0 plus, the function at 0 plus the first derivative at 0 times x plus the second derivative at 0 over 2 factorial x squared, and so on, it's going to be quite awful to find the derivatives of that creature. Instead, since we already know what the Maclaurin series is for the sine of x, we're going to use that instead. So I'm going to pull off the 1 over x first. 1 over x times the sine of x. Well, the sine of x we know is an odd function. I like to remember it that way. So we're going to have the odd powers. We'll have x and we'll have x cubed. X cubed, however, is divided by 3 factorial. X to the 5th is over 5 factorial. X to the 7th would be minus x to the 7th over 7 factorial, and so on. Okay, you can do that in the summation form, but I prefer to do it like this. Now we can distribute the 1 over x through to each term. So, like so, and we end up with 1 minus x squared over 3 factorial, because the 1 over x that we distribute will reduce with the x cubed, giving us x squared. Each power actually will go down by 1. So we'll have plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial. So that would be the Maclaurin series for that function. In summation notation, it is of the form x to the 2n. That's the exponent, or the exponent is 2n. A negative 1 to the n will do for us because we're going to start at n equals 0. You can verify that because when n equals 0, we have x to the 0th, which is 1. Negative 1 to the 0th is positive 1. In the denominator, however, we don't simply have 2n factorial. In fact, the denominator is 1 more than the numerator before we take the factorial, so that would be 2n plus 1 factorial. The great thing about this is we can now use this to answer a wonderful question about limits. If we want to look at the limit as x approaches 0 of sine of x over x, which is something you probably dealt with in Calculus 1, we can do instead the limit as x approaches 0 of the Maclaurin series, which would give us 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial x to the 6th over 7 factorial, and so on. And now it's really easy to see what this limit is going to be, because as x goes to 0, x squared over 3 factorial becomes 0, so does x to the 4th over 5 factorial. Everybody goes to 0, and so we just end up with a limit of 1. That's what you learned in Calculus 1, but we've used Maclaurin series instead. Here we have another one that's really kind of wild. Same sort of idea. We want the limit as x approaches 0 of that crazy mess. In these kinds of problems, what you want to do is you want to find the function whose Maclaurin series we know, like the cosine of x. We know what it is. So I'm going to do this off to the side to save a little space, but we end up with the limit as x approaches 0. And then 2, well, that's just a constant x squared. Of course, we don't have a Maclaurin series for that. But then we have minus 2 times the cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. Now we're somehow supposed to divide this by x to the 4th. Okay, dividing by x to the 4th, I find that's going to be a little problematic for me, so I'm going to move that division by x to the 4th as a multiplication by 1 over x to the 4th. we get 1 over x to the fourth. And then in the parentheses, we'll have 2 minus x squared minus, so I've made my way from there to there. Now I'm ready to distribute the 2. Okay, so it'd be minus 2, and then negative 2 times a negative will become plus 2 factorial in the denominator here is the same as 2, so that 2 out front and the 2 down there will cancel, so we'll just have plus x squared. When we multiply the negative 2 by the x to the fourth over 4 factorial, it'll be minus 2x to the fourth over 4 factorial, and then it'll be plus 2x to the sixth over 6 factorial, and minus the next one, and so on. Now, what's wonderful about this is we have 2 minus 2, which is 0, negative x squared plus x squared, which is 0. If we distribute the 1 over x to the fourth that's in front of all of this, we'll take all of the powers down by 4. And we'll get the limit as x approaches 0 of, okay, all the powers decrease by 4. Well, that would just become minus 2 over 4 factorial plus 2x, well, we went from x to the sixth, we're dividing by x to the fourth, so 2x squared over 6 factorial minus, the next one would actually be 2x to the fourth, I believe, because we would have been at x to the eighth. When you divide that by x to the fourth, you get x to the fourth. That would be over 8 factorial, and so on. And this is wonderful because now as x goes to 0, we have lots of terms that will be 0. In fact, all of them will be 0, with the exception of the very first term, which we get to keep, and our final answer is negative 2 over 4 factorial, which is negative 2 over 24, or negative 112. Our next example is going to take a little bit of work here. We want to find the Taylor series for f of x, which is 1 over x cubed, or, if you will, x to the negative 3. We'll use that in a little bit. Centered at a equals 2. So that's a slightly different experience than we've had so far. All of our centers have been 0. We've been looking at Maclaurin series. So let's just do a quick review of what the Taylor series formula looks like. It says f of x is the function evaluated at a plus the derivative evaluated at a, not by x, but by x minus a, and then the second derivative at a over 2 factorial, x minus a squared, the third derivative at a over 3 factorial times x minus a cubed, and so on. So we're going to start this off by trying to figure out a formula, or an expression at least, for the nth derivative of f at 2 in our particular case. I wrote a there, but let's go ahead and change that to a 2. Okay? Let's first take derivatives. Now I'm going to once again encourage you to not simplify things, because when you simplify things, some patterns become obscure. So our function is x to the negative 3. The first derivative is negative 3x to the negative 4. The second derivative is, well, I will take into account the signs. It's going to be positive 3 times 4 x to the negative 5. I multiplied negative 3 by negative 4, so it's positive. When I take the third derivative at x, I end up with negative 3 times 4 times 5 x to the negative 6, and I'm starting to see the pattern. The fourth derivative, when I bring the negative 6 down, it becomes a positive 3 times 4 times 5 times 6, and then it's x to the negative 7th. A general formula for the nth derivative might look something like this. Now the original function doesn't quite obey this, but the nth derivative, well, let's observe the pattern of the signs. It is positive, and then negative for the first derivative, positive for the second, negative for the third, positive for the fourth, and we have the idea that it might be negative 1 to the n or an adjustment, but negative 1 to the nth does the trick because the even ones are positive and the odd ones are negative. Now let's look at the pattern before that. With the exception of the original function, they all start off with 3. And then many of them, and we can imagine if n is a really large number, would go 4 and then 5. And then we keep going out. Now, let's see here. At the fourth derivative, we stopped at 6. At the third derivative, we stopped at 5. At the second, we stopped at 4. We're always stopping at the number that's equal to 2 more than what derivative we're on. Fourth derivative, 2 more than that is 6. So we're going to stop at n plus 2. How about the exponent of x? It will be x to the negative, and then notice the exponent is 1 beyond the last number we had, so negative n plus 3. And so the nth derivative, that was just a formula for the general nth derivative. The nth derivative at 2 will be negative 1 to the nth times 3 times 4 times 5 times n plus 2 times 2 to the negative n plus 3. Now I get this question a lot, so let me go ahead and address it here. Sometimes students will object, well, you've got 3 times 4 times 5 here, but I don't have 3, 4, and 5 here in the first and second derivatives. I get that objection. I understand it. But this is just trying to give you a general pattern. What you really should be focusing on is the fact that it's saying we want the product of all numbers from 3 out to 2 more than the derivative we're on. So if I look at this and I say, well, what about when n is equal to 1? When n is equal to 1, we're supposed to go to 1 plus 2. So that would be 1 plus 2 is 3. Oh, we start at 3 and we end at 3. And the first derivative, indeed, we end at 3. When n is 4, for example, we should end at n plus 2, which would be 6. We go from 3 to 6, and that's exactly what we have. We're going to need this formula in the next slide, okay? So we'll put this on the next slide as well. So here, once again, we have the formula I mentioned before for the nth derivative evaluated at 2. And I've also included the formula for the Taylor series about x equals 2, or centered at x equals 2. All we need to do is put all of the little tidbits in. F of 2, if you remember, doesn't quite fit what we have up there. F of 2 was simply, well, f of x was 1 over x cubed. So it'd be 1 over 2 cubed. F of 2 is 1 over 2 cubed. That was the one that didn't fit the pattern, if you'll remember right. 1 over 2 cubed. And then f prime of 2, we had a minus sign, so let's fix that, minus. And then the derivative was 3 multiplied by 2 to the negative n plus 3. N was the derivative we're on. We're on the first derivative. N plus 3 would be 1 plus 3, which is 4, so 2 to the negative 4, which I will put as 2 to the 4th in the denominator there. And then we'll have x minus 2. The second derivative, okay, so the second derivative, we built up an extra factor. We are on a positive one, right, because negative 1 to the 2 is positive. We're going to have two factors here, the 3 and the 4, plus 3 times 4 over 2 factorial, but we also are going to incorporate the 2 to the n negative n plus 3. Well, when n is 2, 2 plus 3 is going to be 5, 2 to the negative 5. I'll put the 2 to the 5th in the denominator. This is multiplied by x minus 2 squared. And we're starting to see the pattern. The next one will have a minus because the previous one had a plus. And then we get an extra factor in the numerator, 3, 4, and 5. In the denominator, we'll have 2 to the 6th. The powers of 2 are going up. We'll get the next factorial, 3 factorial, x minus 2 cubed. And then we'll do one more, plus 3 times 4 times 5 times 6 over 2 to the 7th times 4 factorial, x minus 2 to the fourth. And the next would be a minus. Now, I highly recommend that you pay attention to the instructions of your teacher, your professor. Some may say this is okay. I'm going to go one step further and show you kind of a nice way that this can be simplified more. First of all, I'm going to kind of acknowledge that these factors that we're building up in the numerator are almost like a factorial. Look at the last one there, 3 times 4 times 5 times 6. Well, think of it backwards, 6 times 5 times 4 times 3, and then I really would have times 2 times 1, wouldn't I? If I wanted to complete a factorial, it'd be 6 times 4 times 3 times 2 times 1. So what, 6 times 5 times 4 times 3 times 2 times 1. What I'm going to do is in each term, and maybe even the first one, I'm going to introduce a 2 and a 1 in the numerator. And I'll introduce a 2 and the 1 and a 1 in the denominator as well in order to keep things equal. So this new expression is just the old expression with each term, including a 1 times 2 over a 1 times 2. What's great about this is now the numerators can be expressed as factorials. So in the denominator for each of them, that 1 times 2, I'm just going to compute and say that's 2. So I'll get an extra factor of 2, which I'm going to bump up with the 2 cubed and the 2 to the fourth. So all of the exponents are going to increase by 1 as I go. We've made this simplification, and now I'm going to remember the idea that when we have two factorials, one in the numerator and one in the denominator, like let's say we've got this 5 factorial and the 3 factorial down there, I can remove the top certain number of factors so that things will reduce. So 5 factorial is 5 times 4 times 3 times 2 times 1. The 3 times 2 times 1 is 3 factorial, so I'm going to remove the top 2 factors in the numerator for each of these. I've written this out. For instance, again, I took the 5 factorial, wrote it as 5 times 4, multiplied by 3 factorial, because 3 factorial is 3 times 2 times 1. And then the 3 factorials now will reduce, and that's going to be true all the way down the line. So I've got the 4 factorials. Those cancel. Let's make those red for effect. 3 factorials. Those cancel. 2 factorials will cancel. I even have a 1 factorial, which would cancel with sort of an invisible 1 factorial there. And now the pattern is pretty nice. Look at, let's say, the x minus 2 cubed term. The x minus 2 cubed term in the numerator has a 5 times a 4. That's 1 more than the exponent, or 2 more than the exponent multiplied by 1 more than the exponent. And then it's got the 2 to the 7th in the denominator. So our final answer after simplifying, and we end up with this, which is kind of nice because now we can write it in summation notation. I'm going to have the sum. We have powers of x minus 2, so x minus 2 to the nth. N's going to start at 0 and go to infinity. The denominator of each term has a 2. Let's compare this here. Wow, the denominator is like, for example, 2 to the 6th when it's x minus 2 squared, 2 to the 7th when it's x minus 2 cubed. So it's going to be 2 to the n plus 4. And then in the numerator, we've got this alternating sign. So we've got the negative with the odd powers, the positive with the even powers, which means we want a negative 1 to the nth. And I ran out of room here, but the factors that appear before the x minus 2 to a power are going to be 2 more and 1 more than the exponent. And here is our final sum. Okay, so this was kind of a complex example. Again, watch for your instructor's directions. They may say it's okay to stop somewhere along that line, but it's really pretty when we can see these factorials working to our advantage. And you thought we were done with this problem. Remember, I also asked us to find the radius of convergence. The radius of convergence is going to be found using the ratio test. So let's look at what that limit's going to be. We're going to look at the limit as n goes to infinity we're going to do the absolute value. We're going to take this expression, remember, and we're going to substitute n plus 1 for each value of n. Remember, we do a sub n plus 1 divided by a sub n. So a sub n plus 1 will be negative 1 to the n plus 1, and then n plus 1 plus 2 will be n plus 3. The n plus 1 will be n plus 2, and then we'll have x minus 2 to the n plus 1. In the denominator, the exponent goes up by 1. Instead of having 2 to the n plus 4, we have 2 to the n plus 1 plus 4, or 2 to the n plus 5. Now that was simply a sub n plus 1. Okay, now we're going to do the reciprocal of a sub n. Okay, the reciprocal of a sub n is exactly the term here that's behind the sum, but we're going to flip it upside down. So we have 2 to the n plus 4 divided by negative 1 to the nth. Then we have the n plus 2, the n plus 1, and the x minus 2 to the nth power. Okay, I'm going to simplify pretty quickly here so we can save some time. Powers of negative 1 will be positive 1 or negative 1 when we take absolute values. It makes no difference. I see an n plus 2 in the numerator of a sub n plus 1 and in the denominator of the reciprocal of a sub n, so I'll reduce those. The x minus 2 to the n plus 1 and the x minus 2 to the nth, those will reduce, and we just end up with x minus 2. And then when I reduce the 2 to the n plus 4 and the 2 to the n plus 5, we'll just end up with a 2 in the denominator. So our limit is now looking like this. Limit as n goes to infinity. Absolute value, well, we don't really need that except for one little bit. We'll have n plus 3 over n plus 1. Those were the surviving linear pieces. We had, from the reduction of the 2 to the n plus 5 and the 2 to the n plus 4, will have a 1/2 that we need to multiply by. And then we still have the absolute value of x minus 2. As n goes to infinity, the n plus 3 over n plus 1 will approach 1. And so we end up with 1/2 of the absolute value of x minus 2. We want to set this less than 1. The ratio test, you test whether or not things are less than or greater than 1. When we multiply by 2, we get absolute value of x minus 2 is less than 2. So that means my radius is 2. Okay? Now I'm going to give you a sort of gut feeling way of checking that. Our function, if you remember, was 1 over x cubed. We did the center at a equals 2. So the question is, where do I have a problem with my function? Where does the function 1 over x cubed have a discontinuity? Well, if x is equal to 0, we are in big, big trouble because we're dividing by 0. How far is our center from 0? Well, it's 2 units away from that. And again, this is not quite the reason for this, but because it's 2 units away, that's kind of why our radius is 2. It's not necessarily a foolproof method, but it's a pretty good way to get a fundamental understanding of that. The final series for which we have a nice formula for is the binomial series. And the binomial series is kind of odd, but it's very, very powerful and a quite useful one at that. If we want to look at 1 plus x to the power k. Now k can be a whole number, so it could be like 1 plus x to the 5th, 1 plus x to the 11th, that kind of thing. It could be a fractional power, like 1 plus x to the 3/2, 1 plus x to the negative 4/5. You can have all sorts of crazy things for that value of x. Well, it's going to be equal to this crazy symbol, k choose n. Don't worry about that. We're going to define that in a moment. Multiply by x to the n. So what exactly is k choose n? If you want to, you can look down here. Here, the n factorial that appears from the Taylor series formula is built into this symbol k choose n. So there's the n factorial. What about the numerator? The numerator, I'm going to start with the top number there, the k, And then we're going to pretend we're going to do a factorial and then say, faked you out. I'm going to do k and k minus 1 and k minus 2 until I build up n factors. So, for example, when I have x to the third, I'll have 3 factorial. X to the third will be divided by 3 factorial. That 3 factorial has 3 factors, so the numerator will have 3 factors, starting at the exponent, k, and then decreasing by 1 each time, k minus 1 and k minus 2. For this example, we'll just kind of write out what the terms will look like. The analysis with the factorials will be very similar to what we did in the previous example. Here, we will acknowledge that we have replaced x by 5x. Do you see that? Our formula says we can look to see what happens with 1 plus x, but we have 1 plus 5x, so we've made that little substitution. We also need to know the value of the exponent. Our exponent is negative 3, so k is equal to negative 3. Okay, and so we're ready to roll. 1 plus 5x to the negative third power will be, well, it's always 1 plus k times x, whatever x is. 1 plus k, in our case, is negative 3. X, we've replaced by 5x, so it's multiplied by 5x. And then plus, so we've taken care of the first and second terms, 1 plus kx. Now we're going to do k times k minus 1 over 2 factorial x squared. Our value of k is negative 3, so negative 3 times negative 4 over 2 factorial multiplied by 5x quantity squared. Now we're ready for the third term. In the third term, we have k multiplied by k minus 1 multiplied by k minus 2 over 3 factorial. So ours is going to be plus negative 3, negative 4, negative 5 over 3 factorial multiplied by our 5x to the third. And then we would continue. Okay, so you can see this is similar to the last example that we did. We're going to have these negatives accumulating, negative 3, negative 4, negative 3, negative 4, negative 5. So this one here, the x squared term is going to be plus, this is going to be minus. I'm just going to do a little simplification here, but what we could have is we would have 1 minus 3. I noticed a little mistake here. There is a negative I wrote here which shouldn't be there. And then we're multiplying by 5x. And then it's going to be plus 3 times 4 over 2 factorial times 5 squared x squared. And then we'll have a minus 3 times 4 times 5 over 3 factorial times 5 cubed x cubed, and so on. So again, if you want to write this in summation notation, you can use the analysis that we had in the previous slide. We're going to look at an application of the binomial series. In particular, we're going to use our Taylor series to estimate the square root of 9.12 using our Taylor series expansion. In this case, I'm going to write this as 9 plus x to the 1/2 power. Okay, now if I think about the Taylor series for the binomial series, it was 1 plus x to the k power. So we're in kind of a pinch because it's 9 instead of 1. We've done this in the past. What I'm going to do is I'm going to factor out a 9. If I factor a 9 out, that would be 9 to the 1/2 multiplied by 1 plus x over 9 to the 1/2. I mean, you can imagine that the exponents don't appear there. 9 times that business. If you distribute the 9 through, you'd have 9 plus x. Well, now let's put those exponents back on, 9 to the 1/2, that to the 1/2, which is really just 3 times 1 plus x over 9 to the 1/2. Okay, so in our case, we have replaced x by x over 9, and our value of k is 1/2. Now we appeal to the formula for the binomial series, which says that 1 plus x to the k, 1 plus x to the k is 1 plus k times x plus k times k minus 1 over 2 factorial x squared, k minus 1, k minus 2 over 3 factorial x cubed, and so forth. So for ours, we'll have this 3 that's dangling out front. So we've got the 3, and then it's 1 plus k. Our value of k is 1/2 times x. Our x has been replaced by what? What is our x? Our x has been replaced by x over 9. And then we're going to do k times k minus 1 over 2 factorial. We're going to put the 2 factorial down here. K is 1/2. K minus 1 would be negative 1/2. And then we'll have x over 9 squared. Okay? And then we'll have something over 3 factorial times x cubed. Well, x has been replaced by x over 9. That'll be cubed. And then in the numerator, we have 1/2, and then negative 1/2, k times k minus 1 times k minus 2. Subtract 1/2 again, negative 3 over 2. Oh, since that was so sloppy, we'll give you one more. So then it'd be plus, let's see here, I got 1/2 times negative 1/2 times negative 3/2 times negative 5/2 over 4 factorial x over 9 to the 4th, and so on. I'm going to close the parenthesis because remember we have that 3 out in front. Let's distribute the 3 through, and we'll also take some of those fractions raised to powers and simplify them. In the process, I did one other simplification. So I've distributed the 3 through to each term. 3, 3, 3, 3, 3. I also got rid of the fractions within fractions. Let's take a look at the last term that's there. We have 1/2 times negative 1/2 times negative 3/2 times negative 5/2. Well, you've got 1, 2, 3, 4 factors of 2 in the denominator, so I moved those to the denominator of the whole fraction. Okay, so that's where the 2 cubed came from. It came from the 2 times 2 times 2, and the 2 squared came from those two. Okay. Well, now we want to use this to estimate the square root of 9.12 accurate to 5 decimal places. Now, how in the world am I going to do that? Well, let's observe the signs of these terms. Now, it depends on the value of x, but in our case, we're going to be good. So this is a positive, that's positive. Oh, suddenly we have a negative. So it goes plus, plus, minus. And then I have 2 negatives, so that's another plus. And then I have 1, 2, 3 negatives, so those will multiply to give me a negative. So it doesn't quite start off as an alternating series, but it turns into one since it goes plus, plus, minus, and so on. So it's an alternating series. What I'm going to do is I'm taking advantage of the fact that I've got the square root of 9 plus x. I need to find a value of x that would give me radical 9.12. Well, of course, that's just the square root of 9 plus 0.12, which means I'm going to let x be equal to 0.12. And we end up with this alternating sum. Okay, lots of things are making these terms go to 0 very quickly. I have, for example, in this term here, I've got a 2 cubed, a 3 factorial, a 9 cubed that are making all of those very small. And then I take 0.12 to the third power as well. So if you remember, the alternating series estimation theorem said a partial sum for an alternating series is only as accurate as the first term that we don't include. So what I'm going to do is I'm going to find the first term here that is pretty small, and then add all of the ones that are before that. And I found that the term actually that we were focusing on, this term here, when you calculate it, turns out to be quite small. In fact, when we go to the 5th decimal place, 1, 2, 3, 4, 5, the first place that's a little bit even exciting is 2 places to the right of that. So if we calculate the partial sum consisting of the terms prior to that, we'll get an estimation for the square root of 9.12 accurate to 5 decimal places. We end up with 3.01993.